Hi. During the last section of the lecture, I ended up by saying I was going to introduce you to the mesh grid command. I should have said the mesh grid command, which is a command that is useful, especially when you ended up plotting complex figures like three-dimensional figures. But it's also useful to create new matrices from a given array. So I have this little script here that shows the basic uses of these mesh grid commands. And like I mentioned before, this command is going to take two input vectors. In this case, I created two input vectors. And it makes two-dimensional matrices out of it. And what we have is that the resulting matrix will have a number of columns equal to the number of elements in the first vector, in this case, x. Excuse me. And a number of rows, which is going to be equal to the elements on the second input vector, in this case, y. So in this particular example, you're going to have, you obviously have 4 elements in x and 5 elements in y. So, you know, you're going to create a matrix that has that number of columns, x columns, 4 and 5 rows from this two arrays. So this is useful to create rectangular grids out of a given two-dimensional arrays. And as you will see in the next example, it's very useful when you create, for instance, the axis, when you define axis in particular plots. It's a very efficient way of doing that. So let me run this. By the way, I wanted to show you that if, for instance, you have a section on a script or on a piece of code that you want to just comment out in sections, you can select whatever you want and then just click on comment here, and it'll comment out, you know, whatever section you selected. I find that very useful. At the same time, if you change your mind and you want to just not select something or not comment on it, you can click on this X, and it deselects that section to make it part of the code again, and it's not commented out. So I found that very useful. So I'm going to comment this again because it's not part of the code. And I'm going to run this little script, and I'm going to create a set of two matrices, x1 and y1, from the two input vectors using the mesh grid command. Okay, so let's run it. And as you can see, these are my two original vectors, and it created two matrices, okay, of equal size. And it has, in this particular case, it's going to have 4 rows determined by the number of elements in X. And I'm sorry, 4 columns determined by the number of elements in X, and 5 rows determined by the number of elements in Y. So it's a very useful command. As you can see, everything is really repeated, but in this particular format. Okay. And one of the uses for this is, if you look at this, I'm not particularly interested for you understanding how we're generating the plot, but I'm more interested in you seeing what the mesh grid is doing to the axis or the axis of the plot. In this case, it's going to create an axis from -4 to 4 in increments of 0.4 on both A and B. Okay. On matrices A and B that we later use to generate the plot. So let me run the second section, and you can see the plot at the minute. So let me just make sure you have it. So now you can see the plot, right? And again, what I'm interested in is not so much how we generated this plot, but how we generated the axis information that we wanted. A very efficient way of generating this kind of information. So you'll see later how we use this. In fact, there's also a similar command in Python, and when we look into Python, we're also going to see a command that is used for the same purposes. Especially important when you want to create new matrices from vectors, and when you want to use that information for plotting some data. So let me get rid of this and come back. Okay, so we're back. Let me now talk about a couple of things we can do with get rid of this. A couple of the things we can do with matrices, and one useful command, two useful commands are the flip LR command and the flip UD commands, which are used to flip either rows or columns in a matrix, and that can be something that can be useful. For example, I'm going to generate a matrix A, just to random numbers, just to show you the idea here. So this is a 4x4 matrix, and if I use the flip LR command and apply it to the matrix, it's going to flip the matrix A into its mirror image from right to left. As you can see, right, this column here, right, and this column here were basically flipped, right? It's actually the mirror image of everything, as you can see, right? Everything is flipped to the mirror image. So this column here is now located here. This column is located here. And same thing with the rows, right? Everything is flipped onto the mirror image from left to right. That's what's called a flip left, right, A. Okay, a very useful command for doing certain things with matrices. We also have a flip UD command. And if I apply it to the same matrix, it's going to flip the matrix vertically. If you look at the original matrix, which is this one on the top, okay, see how using the UD command, flip UD, is flipping the matrix vertically now. Okay, instead of left to right, it's just flipping it in a vertical orientation. So this could be useful in a lot of cases, as we'll see later, to manipulate matrices. The other one I want you to remember is when you look at the number of elements in a matrix, of course, we can use the size to determine the size of the matrix, right? It's a 4x4. But if you want to look at the number of elements, and from this you can deduct, induce rather, that the number of elements you can have in the matrix. But you also have the num or num el command. Num el command. If I apply that to the matrix, it gives you directly the number of elements in the matrix. Okay, so that can also be useful. All right, so what I want to do now is go over some exercises with you, and what I would like for you to do is to have MATLAB open, and let's run these exercises together so that we we understanding how to do these operations. So the first thing I want you to do is to create just a vector A with numbers 12, 17, 3, and 6. Okay, and then another vector B with elements in a 3x3 actually, with elements in the first row 5, 8, 3. Second row 1, 2, 3, and third row 2, 4, 6. So that's the second matrix that I want you to generate. I want you also to generate a third matrix. We call that C, and that matrix will have elements, just one column with 3 elements. 22, sorry, 3 elements in the columns in the one column. Excuse me. 22, 17, and 14. I'm sorry, 4. 22, 17, and 4. So that's the third vector that I want you to generate. So now we have 3 vectors, A, B, and C. as indicated. So the first thing I want you to do is to assign, create a variable, let's call it x1, and I want you to assign the value in the second column of matrix A. So matrix A, or vector A, right? In this case, I want you to store the value in the second column of matrix A. In this case, this column here, right? Into this variable x1. Okay, so we want to assign value of the second column of A to a variable that we're going to call x1. All right, so I'll give you a second or a minute for you to do that, and you can pause the video and I show you the simple solution. And again, the way we can do this, of course, we're going to have the variable x1, and I'm going to assign the particular element that I want in this case. And there's more than one way of doing this, okay? But this will be the quickest, I guess, or one of the quickest way to do it. So by selecting, using the subscripts here, 1, 2, I'm selecting that element in the first row, second column. So that assigns the value of the second column to the variable x1. Next thing I want you to do is to assign to a new variable x2. So we want to assign the third column, in this case, the whole column of B to a variable x2. Okay, so we're assigning the third column of B, so this is the third column, just to a vector variable x2. Okay, again, give you a minute, but I'll show you right away how that's done. So x2 is the variable that I want. So I want to go, if you remember, I want to select all the rows, really, right? And in this case, since I want all the rows, but I'm focusing on the third column, then assigning that gives me the third column of B, right? So I really just use this to select or say, well, take a look at all the rows, and for every row, select the element on the third column, right? All right. The next exercise I'd like you to do is to assign the third row of the matrix B to a variable x3. So assign the third row of B to x3. So B again, you still have it on the screen, is right here, right? So we want to assign this third row here to this variable x3. Okay, so the way we can do this is have a variable x3, and I'm going to assign from B, actually the opposite of what we just did, right? Because now I'm focusing on just the third row. Again, as you can see, that's the third row B, which is assigned by this simple command. Okay, so the next one I'd like you to do is to assign to a new variable x4. So on this one, I'm going to assign the values in B along the diagonal. So when I assign all diagonal elements in B, and we want to assign that to a variable x4. Okay, so again, when I assign all the diagonal elements, there's more than one way of doing this, and again, I'll show you later how can this be done in more than one way. And this may not be, and again, if you come up with a different way, it's perfect, as long as you get the results. And this may not be the most efficient way, but you could simply select the elements individually and assign them to the variable, right? So you can go, well, B1, 1 is the first diagonal element. And then you have B2, 2 is the second diagonal element. And then obviously B3, 3 is the third diagonal element, right? And that will give you the specific diagonal elements from here, right? Of course, if you do, this, right, diagonal will give you that too, right? But we wanted to, just show a way of doing it by accessing the values in B with a particular subscript associated for that element. So, right, same result, but just showing you what that means. Okay, the next exercise is I want you to assign to a new variable x5. So we want to assign to x5 the first three variables. Well, the first three values, I should say, not variables because the matrix has values. The first three values in A as the first row, and all the values in B as the second through the fourth row. All right, this is a little more challenging, I think. You expand on this a little bit. Expand it a little more. All right, that's better. So we want to assign to a variable x5 the first three values in matrix A as the first row, and all the values in matrix B as the second through the fourth row. Okay. So again, there might be more than one way of doing this. If you done it differently, it's fine as long as you get the results that the exercise is asking you to get. So let's try that out. One way of doing that, I have x5, and I'm going to assign to that. I'm going to extract from A. I'm going to get the first row because I want the first three values in A as the first row, and then from B is just B, right? Because that's what I want as the second through the fourth column. So doing that, as you can see, I have what I was intending to do. I have, if you look at A, let me bring back A. All right, that was A. So I have the first three values in A, right? The first three values in A as the first row in my new matrix X5. And then I should have, and let me bring B again, what B was. I have all the values in B, which is all this matrix that form the matrix 5 from row 2 through 4, right? So first row came from A. The next three rows came from B, and that's the command. Okay. All right. One more. On this one, I want to assign to a new variable xc the values in matrix C as the first column, then the values of B as the second column, as columns 2 and 3. So let's see, the values of B as columns 2 and 3 and 4. So 2, 3, and 4. And one more thing, and the values in A as the last row. All right, again, interesting. Let me make more space so you can read that. All right, so we want to, okay, so this is the exercise. We want to assign to a new variable x6 the values in C as the first column. So the first columns are the values in C. The values of B as columns 2, 3, and 4, and the values of A as the last row. All right. So again, you can stop this and I'll give you the solution. And one possible solution is, okay, I have variable x6 and I want to assign to x6, the command to do this will be, I want C, right? That's the first column. And then the rest, I really just want B. And I want to go through A, right? So, oops, sorry about that. I think the problem is that I'm missing a comma here. Sorry about that. Semicolon. All right, there you go. And as you can see now, we have, and let me bring back the matrices. B is visible, C is not visible. Let me bring C back. All right, so we have to x6 is the new matrix. We have the values of C as the first column. So C is right here, right? Values of C, right? That's the first column. And we have the values of B as columns 2, 3, and 4. So values of B, right? Values of B is the columns. We transferred the columns from B into here, right? You can see right here. And then we added one row. And the last row is the values of A, right? So we constructed the new matrix X6 from all the elements in C, right? We put all the elements in C here, and then we added the elements in B here, and then we added as the last row the elements in A. Okay, so that's the command that you can use to do something like that, to manipulate the matrices. And it's not the only way, right? You can put a matrix within a matrix, right, to create things that you want. For example, if you can put these two matrices together by just a single command, but that's, again, is one possible way of doing it. Let's do another one. So on this one, I want to assign to x7, the new variable x7, the values of, or the value, I should say, because it's 1, whatever it is on element A, 8, a matrix B, and I want to use the single index number identification. So I want to assign to a new variable x7 the value of element 8 in matrix B. Matrix B is here. So remember how this goes, right? It goes from 1, 2, 3, 4, 5, 6, 7, 8, right? It's got 9 elements. So I want to assign the value of element 8 in matrix B. And I just want to use the single index number. In other words, let me do it first, right? So it's very simple, because if I just want to assign that element, right, I'm simply going to assign the value in that element, right, which is 3, as you can see. Now, the other way we could have done it is by simply going, well, this element is in row 2, column 4, right? For C, this is B. Where is B? I'm sorry. I was looking at the wrong one. That's B, right? So the 8th element is also given by the second row, third column, right? So if I look at the second row, third column, it's also that same number, right? Right. But this shows you again how you can access numbers by using the single index identification. For instance, if I want to select the 9th element in B, which you already see here is 6, is simply just selecting that by a single number, right? And it's 6, which is also the same number that I could get by saying B 3, 3, right? It's the same number. So that's one thing to know. One more thing, let's see. The next one is I want to convert matrix B to a column vector. And I'm going to call a column vector x8. So I want to convert matrix B, right? Matrix B is right here, to just one column vector. Again, there's more than one way of doing this, right? And hopefully you figured out more than one way of doing it. But one quick way is just to assign x8. It's just be that, and then all of the columns, rather all the matrix B become just a single column, right? All right. And this is simply because it's going one by one. It's saying, well, every element in B, right, for every column and for every row, assign it to the new variable. The next element, assign it to a new variable, one by one. Basically, that's what you're doing when you use this command, right? All right. Let's see. We still have some time, so let's continue with a new one here. In this one, I want you to create a matrix with, and this is a 4x6 matrix. Let's do a 4x6 matrix. And in this matrix, all the elements equal to, we're going to have all the elements equal to pi. Okay. So we want to create a matrix 4x6 with all elements equal to pi. Well, again, not the only way you can do this, but it can show you one way that you can use, for example, the ones matrix. For one thing, remember, if I do ones, let's just do, I don't know, 4x4, it's going to create a matrix of just ones, right? So if I want to do the same thing for a 4x6, right? And to that, if I want to do the this to create all elements equal to pi, I can simply take that and multiply by pi, and now all the elements have a 4 by 6 with all elements equal to pi. Okay. Now again, there's not just one that way of doing it. For example, if you remember, I can also create zeros. So I can create a matrix of 4 by 6 zeros. And if I then just take this and add pi to it, I can also, I'm doing the same thing. And there's other ways that you can do this, obviously, right? But it shows you a way of using zeros and the matrix of zeros and the matrix of ones to do something like that. All right. Let's see. What about this one? Let's see, try this one. It says we want to use the diagonal command or function to create a matrix with just diagonal elements of, let's give it 1, 2, 3. So I want to create a matrix with diagonal elements 1, 2, 3. Okay. So one quick way is to just assign the elements to an array, right? Like I did previously, just 1, 2, 3, and then just use the diagonal, and that will create the diagonal matrices or the matrix with diagonal elements 1, 2, 3. Okay, it just takes this vector and creates a diagonal matrix with the elements of that vector. Okay, it's kind of simple. So we've done exercises with extracting diagonal elements, so that's not unusual. Let's do one more with diagonal matrix. Let's create a magic matrix 5 by 5. And I'm going to call that C. So I have a 5 by 5 matrix, magic matrix. And what I want to do now is I want to extract the diagonal element, just the diagonal elements. Remember, if I do diagonal C, I can see all the diagonal elements from left to right, right? 17, 5, 13, 21, and 9. But now I want to go from left to upper right this time, right? So instead of going in this direction, I want to extract the elements in this direction, right? And that's when it comes something useful like the flip function comes in place, the flip left right. Because if I do, I take diagonal and include the flip LR to the matrix, now you can see I extracted the elements 15, 14, 13, 12, 11, right? In the other diagonal direction, right? So this itself gives me the elements, going from left to right, but this one is going from right to left by doing this, by flipping it. Because what I've done, if you look at just the flipping part, if you just flip, right, oops. Right, by flipping the left, right, see what happens, right? I just mirror image this. So it's really kind of a trick because I first flipped it and then I just applied the diagonal. to extract the elements as usual, right? In this case, it's be 15, 14, 13. So the diagonal, really just goes that way, right? But what I did was just flip it first, so it keeps continuing in the same direction, but with it, I extracted the elements in the original matrix in that direction. Okay, a couple other things. Remember I showed you before how the magic matrix, the idea is that all the elements add up in any direction. So you can use, and we did this before, right? Sum of all the elements in C are 65. The sum of all the elements along the rows are 65. The sum of all the elements in the diagonal are, I'm sorry, I'm missing here. Is C, not X. Sorry about that. I'm using C. It's 65, right? So, and if we do it on the other direction, I can use the statement that I used before, which is this one, right? And if I add the elements in that direction, which now is in the other direction, right? It's also 65. So, with that, I went the sum of elements along the columns, sum of elements along the rows, sum of elements along the diagonal this way, and the sum of elements along the diagonal that way, to corroborate that, this is a magic matrix. So even if I didn't know what the numbers are in the matrix, this is a way of checking that the matrix C in this case is a magic matrix, right? All right, let me then start talking about complex numbers. All right. So we can define complex numbers by simply using the letter I or the letter J. In MATLAB, you can use either letter, okay, to define a complex number. So for example, if I have x equals, let me go back here, x equals 2 plus J1, oops, sorry. MATLAB is picky about that. Let's see, what am I missing here? Oh, I see. Okay, sorry about that. If we just say x equals 2 plus, I was missing the plus, 2i, it creates a complex number in rectangular coordinates, 2 plus 2i. I can also use j, and it'll recognize it as I. Okay? So it doesn't matter. We can continue using j as we do in electrical engineering, and it'll recognize it as an imaginary number. I can also do the same thing if I use the command complex. If I use complex and I do 2 comma 2, it's gonna create the same result. It's gonna give me x as a complex number, 2 plus 2j. I can extract real and imaginary parts. So the real part of x is by just using real x. The imaginary, using emag of x, gives me the imaginary part. And let me use a different number so we can identify the better which one is which. So I'm going to have 4 plus, I don't know, 15j, right? So again, if I want to look at the imaginary part, this case is given by 15. If I want to know the absolute value or the magnitude, I use ABS. And so the magnitude of that complex number is given by typing using ABS. I can also create or look at the conjugate by using CONJ with the number that I have, or the variable that I have, and this creates the conjugate of X, right? If S, X has a positive imaginary part, so the conjugate is going to give me a negative. To get the angle, I use angle with X in this case, which is the variable I created, and it gives me the angle, or it gives me the angle in radians. So, you can just multiply that number by 180 over pi. So if I just take X, angle X rather, let me assign it to a variable. I'm going to call that variable X, X1. So now X1 has the angle. So if I want to represent that angle in degrees, I'm going to have to multiply by 180 and use parentheses to make sure 180 over pi. And now the angle is in degrees, 75.0686 degrees. So that's how you extract information from a complex number. And that's how you put the base in radians if you need to. Okay. We can also, if you look, for instance, let's create another array here of complex numbers. In this case, I'm going to have 1 plus 2i. I'm going to have also, let's create it with more elements than that. I'm going to have 3 plus 4j or 4i. And I'm going to have 3 plus 5i. I'm going to add one more. And I'm going to have 9 plus 3i. And maybe let's add a negative imaginary number somewhere in here so we can, see the differences. So in this case, I've created this array of, it's a 4x4 matrix, right, with these elements associated with each of the elements in the array. For example, if I want to just see how they look like, well, first of all, I can then, if I type ABS for the matrix, it's going to give me the individual magnitude for each of the matrix elements. If I do angle again, I can do, it's going to give me the angle in radians for each one, just like before. I can also, if you wanted, you can plot it. In this case, we're going to use the plot command, and I'm going to assign to each of the elements in the matrix, I'm going to assign just this character so we can see it. Now you cannot see it probably this time, so let me make sure. Okay, so now you're seeing what I plotted. And all this does is just showing you the location of the complex numbers that we had in the matrix, right? If you don't remember, these are the elements here. 1 plus 2j, 3 minus 4j, and so forth. This is just showing you the locations, right? Nothing fancy on that. There's one way for you to see where the numbers end up. Okay. All right. All right. So if we now want to convert to polar coordinates, let me clear this up. There's a simple command to do that. So to convert to polar, you use the cart to pole command, and what is called CART to number 2 POL. Okay, that's the command to convert from rectangular to polar coordinates. And what it does is it's going to give you a result. It's going to give you two results, which is going to give you the real part and the imaginary. I'm sorry, the angle and the amplitude. Okay, so if I do, for example, for the matrix that I had before, let me do this for x. What we have for x? Yeah, that's what we have for x, right? So we want to convert this matrix to polar coordinates. And I'm going to assign it to two matrices. I'm going to call one P and one Q. I'm going to use cart2pol for the real part of x. I'll tell you the real part of x and the imaginary part of x. And so I'm going to take the real part of x, the imaginary part of x. I'm going to use the cart2pol, and I'm going to assign the results both to P and Q because I have, right, I'm going to have an angle and an amplitude, right? If I do that, as you can see, this P now has the angles, and this second matrix has the magnitude. Okay. I can also, you can use the reverse, right, to convert polar to rectangular. To convert polar to rectangular, you use the POL2 cart, okay? And we're going to use it now. So now, again, this is going to give me a real part and an imaginary part in two different vectors or matrices. So I'm going to assign, in this example, I'm going to use lowercase a and b for the real and imaginary parts. That's what the real and imaginary parts are going to go. And I'm going to use pol2, number 2, cart, from polar to Cartesian coordinates or regular coordinates. And I'm going to use the previous values that I have for P and Q. And as you can see now, I get back, right, the original numbers that I have, right? For the real part, I have 1 and 3. This, if you can see here, this is my original matrix, right? I have 1 and 3 for the real part, and 3 and 9 for the real part, which is what you have here. And for the imaginary part, I had 2, 5, minus 4, and 3. So the imaginary part, again, is 2, 5, minus 4, and 3. But this came directly from the conversion that I have from the angles, or from the polar coordinates. All right. So that concludes the lecture, and we'll see you next time.